Choosing 2 out of 4 alphabets is 4 choose 2, which equals 6. Then, what is pi choose 2? The formula we normally use for combinations works perfectly whenever n and r happen to be natural numbers. In this example, plugging in n equals 4 and r equals 2 gives us 6. But now, we're trying to compute pi choose 2. This is the case where n is irrational, not a natural number. So, the standard formula simply breaks down. We need a deeper, more general idea. Still, we can estimate the rough range of pi choose 2. 2 choose 2 equals 1. 3 choose 2 equals 3. 4 choose 2 equals 6. 5 choose 2 equals 10. Look at the pattern, and choose 2 grows steadily as n increases. Since pi lies between 3 and 4, if such a value exists, pi choose 2 must lie between 3 and 6. Let's check it out. What we need is a version of combinations that extends n from natural numbers to real numbers. Surprisingly, such a formula was discovered over 300 years ago by none other than Isaac Newton himself. How did Newton come up with such a formula? The key lies in the binomial theorem. In the classical version, n and r must be natural numbers. When you expand 1 plus x to the power of n, the coefficient of x to the power of r is exactly n combination r. This formula can also be expressed like this. You should remember this expression. Newton wanted to extend this idea so that the exponent n could be a fraction or any real number. He began with the expression 1 plus x to the 1/2. Let's call this y. Then y squared equals 1 plus x. Newton assumed that y could be written as an infinite series. Then he squared this series. And matched each coefficient with the corresponding term in 1 plus x. A squared must equal 1, so a equals 1. 2ab must equal 1, so b equals 1/2. 2ac plus b squared must equal 0, so c equals minus 1/8. Similarly, d equals 1/16. This gave Newton a complete infinite expansion. Essentially, the Taylor series of 1 plus x to the 1/2 around x equals 0. He examined these coefficients closely and realized that they could be written in exactly this form. Do you remember this expression? It is a kind of combination formula. It was the same structure you get when you substitute non-integer values for n in the combination formula. N was no longer restricted to natural numbers. This is how he built the generalized combination formula. Let's apply this formula to pi choose 2. Plug in alpha equals pi and k equals 2. It gives approximately 3.364, which fits perfectly between 3 and 6, just as expected. With this formula, you can easily solve all kinds of other problems as well. Thanks to this formula, we can compute values like pi choose 2, something that otherwise would seem impossible. And this generalization turns what used to be just a scatter of discrete points into a smooth and beautiful curve. Newton delivers once again, but this naturally raises another question. Newton generalized combinations by extending n to real numbers. Then, what about r? Can we make sense of expressions like 3 choose 1.5 or 6 choose pi? For combinations to be fully generalized, r must also be extended to real numbers. Mathematicians have already developed a fully generalized version where r can also be any real number. Wanna know how that works? Comment yes and subscribe. I'll walk you through it in the next video. Thank you.